This episode documents the database underneath our molten salt reactor simulation. We'll cover how it was built and what else you can use it for, like the graphic shown here. The database was designed to be simple and robust enough to support future expansion of the simulation. We'll conform to modern database design principles, but we won't be fanatic about it. First, we'll look over the internet to see what data are available. If certain data are not available, we'll need to develop it. Even the unavailable data will affect the design of the tables. We want the table structure to be robust enough to handle data we don't have yet. The primary key we will use diverges a bit from formal database design rules, but we have reasons for that. Formatting and importing the data is rather mechanical. Quality control is not. The most convenient data was already in Microsoft Access files at Berkeley. These needed some work, which we'll cover next. The fission yields data started at Berkeley, but the Brookhaven data was more conveniently formatted, and it turned out more accurate. The Tori2 database has a strangely named table with most of the branching data. However, it lacks data on decays that end in metastable states. The International Atomic Energy Agency has data on that, most inconveniently packaged in an uneditable PDF file. We must also mention the very fine NuDat2 website at Brookhaven. It's unusable for mass cut and paste, but for quality control on individual isotopes, it's very friendly. The Tori2 database MDB file from Lawrence Livermore Lab can be loaded directly into Access. We don't need all of it, and it doesn't have all the data we need. The Tori2 table that characterizes each isotope in terms of its atomic number or element, atomic weight, metastable state, and half-life is called parents. I renamed it isotopes. The parents 2 table describes the decay modes and branching ratios for each isotope. I renamed that daughters. The initial fission yield data, which describes several fuels and neutron energy levels, is from Brookhaven. The sums of the branching ratios do not always equal 100%, especially when neutron emission is involved. Physicists probably have a reason for that, but it is inconvenient for me. There is also some redundancy, which is not as big a problem as with other databases. The problem is worse if the data changes a lot, but atomic numbers or element names are not likely to change. The biggest change was in the primary key for the database. Tori2 uses a cryptic integer that multiplies the proton number by 10,000, adds the atomic weight, then adds 300 for each metastable state number. It's hard to work with, but it is unique. The primary key has to be unique, but someone forgot that isotope names by themselves are unique. I'll be using the far more readable isotope names as my primary key. Names will consist of the atomic weight, a dash, and the element symbol. If necessary, this will be followed by another dash and an M and an integer to indicate the metastable state. The working data resides in 3 tables. The isotopes table will also have fields for the neutron absorption and fission cross-sections eventually. Other characteristics that depend only on the isotope might be added. The daughters table will eventually hold decay energies, which depend on the isotope and decay mode. The yields table currently has 5 fuels and 3 neutron energy levels. There is also an elements table. You need that when you want to determine the number of protons, which is not part of the isotope's name. That and the other parsed elements of the isotope name are available in the standard view. We can put this into Excel to create the pretty stacked bar chart on the title slide. It's named the Nepal view for a professor I once had who said he never saw a stacked bar chart that he liked. The user will select the fuel mix and reactor characteristics before each simulation run. These will be saved in their own tables with their own names for the user's choices. The 9th test run here has 8% enriched uranium, The 238 uranium will fission if hit by a fast neutron, so for some reactors it is fuel. The start column is a future enhancement, hence the parentheses. The tar sands 9 fuel mix is the startup fuel here. 2E0 is the name of the snapshot taken after the first second of reactor operation. At the current stage of simulation development, the fuel mix doesn't change, but in the future, the user might alter the makeup fuel as the simulation progresses. Note that the fuel will evolve anyway, so at year 1, or about snapshot 2E25, there will be some plutonium and other actinides in the mix. The denatured molten salt reactor is a thermal reactor. The percentages here are notional and assume that fast neutrons cause at least a small number of fissions. The start column is notional here and again indicates a scheduled change in reactor operations. The neutron energy distribution is primarily a function of the reactor geometry and choice of moderator. However, the salt mix has some moderating effect and might be varied late in the run. This is a low priority model enhancement. The percentages in the reactor spectrum design table come from a more detailed simulation of the core and its neutron histories. These will probably need to be aggregated to match the energies available in the fission yields table. However, at first they might just be notional values for the purposes of a political narrative. Any salt cleaning process will have a name and specify that a given isotope will be reduced by some percentage starting at a certain time. The next and subsequent snapshots will carry that percentage forward. In terms of that political narrative, here is part of a presentation that compares nuclear choices. Our simulation should provide first-cut estimates for the numbers in the blue boxes. These include how much fuel is consumed in tons per gigawatt. For some reactors, some of that fuel will be from current stockpiles of spent nuclear fuel. The original focus of the simulation was waste products, and that can be as detailed as we wish. At this point, we have data of unknown quality. We can test quite a few things in Excel, but first we'll recreate the pretty chart. That's done by creating a pivot table with all the data from the view we talked about, then creating a pivot chart from that. The field list for the pretty chart is arranged like this, which you may not be able to see as I now switch to Excel. The access query provides some 15,000 records and can be easily exported to Excel. Here in Excel, I've turned on some filters to look only at the decay chain for atomic weight 66, specifically for 233 uranium as the fuel, in the thermal region. The bottom record has a yield of 0. Unfortunately, the raw data does not include such records. I had to add them to complete the decay chain, and that quality control task is not finished. Here's the pivot table created from those 15,000 records. I've already set up the field list to match the last slide, and I used the report filters to focus on 233 uranium in the thermal region again. The numbers in the highlighted row should match the 66 chain numbers we just saw. I also started the pretty chart and made it prettier and took a picture of it. Here's the pretty chart. The most popular element on the chart is tellurium, the broad orange swoosh on the right. I do agree with Dr. Neppel that a stacked bar chart can hide things. The various isotopes of tellurium in another chart would show a bell-shaped curve, which is disguised here by the stuff under it. That is easily fixed. Back in PowerPoint with the large print version of the field list for the next slide. This slide also shows some of the results. On the left is silver with fast neutrons. On the right is a possible outlier in the cadmium data. More work for the quality control crew. Back in Excel, here's the first of the isotope distribution charts. It's silver again, but in the slow spectrum. We can change that to match the previous slide. We can also change the element to cadmium and see another outlier. There are about 50 elements in this data set, and usually 3 energy levels, so I have some 150 charts like this. Here's silver at low and medium neutron energy levels. Here's the distribution of silver isotopes produced by a fast neutron, as seen on the previous slide. It's better behaved than the rather ragged low energy level chart. A little variation is not a problem. We can scroll through these charts looking for more outliers or other trends. That's the first rule of data mining. Just look at the data graphically. Excel pivot charts are great for that. Here's a possible gallium outlier. And for gadolinium, why does plutonium produce so much more of that element than uranium does? Farther to the right are the fast neutron distributions. Scroll through these looking for more anomalies. A subtle one is that there are only 4 curves on the right. We seem to be missing fast data for 241 plutonium. Back to the pivot chart for more data mining. Here we won't need the chart. We do need to bring back the field list and rearrange it to look at the fuels and energies available. In this little matrix, we see the gap for uranium-238 at low neutron energies. That's okay, thermal neutrons do not affect 238 uranium. We also see extra data for 239 plutonium that we won't be using. We still have a gap in the 241 plutonium at high energy. This matrix sums all the yields. All of these sum to 2, since 2 smaller nuclei are created every time a fuel atom is split. In fact, these numbers are suspiciously accurate given the uncertainties of the raw fission yield data for each isotope. Changing the data statistic, the records are now counted, not summed. We have about 1,000 rows of data for each combination of energy and fuel, except for the 241 plutonium at 14 million electron volts. I haven't loaded the fission yield data for americium and curium yet, but a look at the raw data shows the same gap. This is a problem. Overall, the project is doing well in the area of database design, and much data has been imported. But we have identified 3 problems: the lack of fast data for the heavier actinides, some outliers in the current data, and gaps where the decay chains aren't complete. It may be a while before I publish this database.